Hi, I'm Sophie. My partner for the lab was Ian, and this is our code overview. So the first thing we're going over is the counter. The counter takes in the clock from the FPGA. It has an input for new hours, new seconds, and new minutes for when you set the time. It has an input set for when you're setting the time, and then it has an output of hours, minutes, and seconds in that order as was specified by the lab. And so for our adding function to increment the clock, we ended up using the adder from the ALU as specified in the lab. We have a +1 function that increments the plus seconds, plus minute, and plus hour by 1 each time. And then we have an always block to say always at the positive edge of our slower clock, so it runs at 1 second every iteration. If the clock is being set, the output is the new times that the clock is setting, and then otherwise at the slow clock, seconds increment by 1, and then when seconds reach 60, minutes increments by 1, and then when minutes reach 60, hours increments by 1, and then when hours gets up to 23, it increments back to 0, so you don't display 24 hours on the clock. And then we're going to have Ian talk about the top module.
Yeah, so I thought we'd talk about the top module that kind of wraps everything together. So it takes in the input from the FPGA, input from the buttons, the set time, reset alarm, and set alarm switches, and then outputs to the anodes, LEDs, and LED segments, and then the LEDs as well. So we have all of the wires that basically take the values from the different modules. But first module we have is the mode selector module, which allows you to select which mode you're in by pushing a button on the FPGA. And then the clock controller module we just talked about has a couple debouncer buttons that debounce the position modifying or toggle button, the add one and the subtract one. Our set time controller takes in all of the values from the buttons and the position, and then it outputs the new seconds, hours, and minutes to the um, counter module. The 12-hour module takes in the hour from the counter and modifies it to be AM PM. Set alarm allows you to set the alarm using the similar functionality to the set time with the addition of the alarm. And then we have our decoder, which takes in based on the current mode, displays the correct outputs and the light for the output mode. The board will have lights and then the 7-second display module. The board will have lights for each of the modes and the indicator for which position you're in. When the alarm goes off, a light will light up on the LED display as well.
Hello and welcome to our project demonstration for the lab number 4, the digital clock. So right now it is in the 24-hour display mode, and if you notice these LEDs right here, 1, 2, 3, 4, will tell you which mode we're in. So you can change the mode by pushing this button here on the FPGA, and it will change to, this is set time mode. And this button over here will do the position of the that you're incrementing, so you can see that changes to hours, minutes, and seconds. So let's go ahead and set the time to something above 12 so that you can see the AM PM feature. So 1300, and we'll set a minute up here. So you can also subtract by pushing this button there. It goes down, and then so you increment the and then the set alarm here. Oh, sorry, that's the wrong button. Set alarm here will allow you to set the alarm. And I would like to point out that the clock, wrong button. The clock does not stop while we are doing the setting. So the clock currently it has not been set to the new time yet, and that is done by flipping this switch. Once that switch is flipped, it sets the clock to the new time. So now at 1300, we switch to the set alarm mode to show the alarm working, we have to set the clock to something after 1300, so we don't have to sit here for 13 hours. So we'll do 1304. You can set alarm by flipping this switch. This is the reset switch, so I'll show in a moment. So then you go back, and then yeah, it's 1 o'clock, 40 seconds, and that's the PM indicator light. So then for 24 hours, we're going to reset the clock, and then the alarm is going off with that light right there, and then if you push the reset button, it resets. And then of course, if the alarm is set and the set alarm switch is off, the light does not go on. And I would like to know that the time is correct. It is 100 million divided by 100 million, 100 megahertz divided by 100 million is 1 hertz, which is by definition 1 cycle per second. So that should be a 1 second accurate clock. Thank you.
And now we're going to discuss some of the challenges and successes that we had. So it was a little challenging to get the clock to be exactly 1 second, and also to work through some of the modules and putting them all together. So once we started, we basically iterated and did one piece at a time, got it working, and then just built on it from there. And then once we got all of the pieces working, we started adding features like the LEDs and other indicators that I thought were pretty interesting additions to it.
It was also pretty difficult to get the counter to work correctly, because making sure the timing incremented correctly with the adder was difficult, but we managed to do it by calling our module outside of the always block and then modifying it based on there as opposed to incrementing by one in the if statements themselves.